Hello, everyone. Thank you for joining our talk. This is Fengze from Purdue University. Today, I'm excited to represent our team, including Ahan and Voiku, to share our work on an approach for extending 360 VR to support viewpoint translation and collaboration without increasing the acquisition cost, and with demonstrated advantage over conventional 360 VR. Virtual reality technology can provide powerful immersive visualizations of real-world scenes, but faces the major challenge of acquisition and construction of a virtual environment to capture the real-world scene in detail. Recent approaches, such as photogrammetry, neural radiance fields, and 3D Gaussian splatting, succeed in creating quality digital replicas of the real world, but all have in common a high acquisition cost due to long acquisition times, high equipment costs, and complex post-processing. On the other hand, one straightforward and low-cost approach is 360 VR. Commodity-priced 360 still and video cameras can allow users to acquire the real world in all directions with ease and provide a strong sense of presence in the real-world scene when viewed immersively in VR. However, 360 VR has several limitations. One is that users cannot translate within the scene, as the user viewpoint is confined to the acquisition viewpoint. You can see here, the user takes several steps in different directions, but their viewpoint in the scene does not change. Another limitation is in collaboration. Since only one user can be at the acquisition point at one time, 360 VR renders the collaborator's avatar at a position that appears spatially inconsistent with respect to the real-world scene. You can see here, when one user goes backwards, in their view, the other standing user who doesn't move slides from the deck to the water. To combat these limitations, we present Terraforma. We began by modeling the ground under the 360 acquisition point with the plenary patch rendered with projective texture mapping on which the user can stand and walk. Then the far region of the scene is rendered with the conventional environment mapping. However, this will cause a noticeable strong discontinuity between the near and far regions. Thus, we extend the ground patch with an intermediate region, which allow us to maintain visual continuity within the scene. Our method requires only defining two parameters, the approximated acquisition height and the size of the ground patch. Then it runs for all types of scenes. Here, we present a detailed overview of our algorithm. The acquisition viewpoint is defined as O and the user viewpoint defined as U. The ground underneath is modeled with a horizontal plenary patch AB. The whole space is thus split into three regions, a near region, an intermediate region, and a far region. The user safe space is set to be smaller than the near region to not be allow the user to go all the way to the boundary of the plenary patch. Now we have a user frame. For any ray that hits the ground in the near region, we sample the panorama by looking at the ray from the acquisition point to the ground point, which is the projective texture mapping. For example, UB here is set by looking up the 360 image along ray OB, which has direction Rn. For any ray that hits the ground in the far region, we sample the panorama normally. For example, user ray UC is set by looking up the panorama along direction RF. Similarly, a user ray that misses the ground plane altogether is looked up along its direction in the panorama. Finally, we have rays that hit the intermediate region, for example, user ray UD here. To maintain visual continuity, UD is set by looking up the 360 image along direction Ri. The direction of Ri is determined as a linear blend of the projective texture mapping ray Rp and the environment mapping ray Rf. With Terraforma, users can then translate in 360 VR, feeling more grounded. On top of that, we integrate virtual objects into Terraforma, while maintaining an agreement in terms of appearance and geometry. The ground patch and its extension partition the 3D scene into three regions: the near region, the intermediate region, and the far region. A 3D point in the near region, for example N, is projected conventionally. A 3D point in the far region, for example F, has to be shifted to a new position F' such that when projected from the user viewpoint U, it lands in the user frame where it would land as it were looked up from the environment map. Ray UF' remains parallel to ray OF. A 3D point in the intermediate region, for example I here, must be shifted to a new position I', in between I and the full shift of the far region IF. The amount of the shift is determined by how close point I is to the boundary between the near and the intermediate region. Here is an example of what a virtual object looks like integrated into the scene across different regions. Given this, Terraforma provides a consistent shared 3D space that allows approximating avatar positions more congruent with a collaborator's positions in the real world. This shared space also allows cross-referencing objects in the near, intermediate, and far regions, as demonstrated here with virtual lasers. Distortion caused by the interpolation in the intermediate regions can be quantified as the angle between the intermediate region direction of the line and the correct near region direction. Here we visualize the distortion in scenarios corresponding to an indoor and outdoor scene with a checkerboard texture. Our measurement shows that Terraforma connects the near and far regions with approximately piecewise linear continuity. In terms of implementation, the ground patch was implemented through a fragment shader, while virtual object integration was achieved through a vertex shader. When Terraforma is run on a standalone Meta Quest 3, it achieves an average frame rate of 72 FPS, which is the refresh rate of the device. To evaluate our research hypothesis, we conducted a IRB-approved user study with 30 participants. Each participant completed 5 tasks for each of 2 virtual environments, an outdoor and an indoor scene, across 2 conditions on standalone VR. We use questionnaire results as metrics. These tasks include free exploration in the scene, moving towards a virtual target in the scene, virtual object selection, viewing a virtual object moving through the scene, and collaborating with a researcher to cross-reference objects in the virtual scene. After each task, the participant was asked in VR task-specific questionnaires, and after each condition, they were asked out-of-VR standard questionnaires to evaluate system usability, presence, and cyber sickness. The finding of the user study supports several of our research hypotheses. Compared to conventional 360 VR, Terraforma's ground patch effectively anchors the user to the ground, providing a stronger sense of physical presence in the scene. Additionally, our method for virtual object integration allows for more convincing integration of stationary and moving objects in the scene. Due to the linear interpolation of the intermediate region, there is a noticeable distortion of the scene and the moving objects. Despite this, our finding demonstrates that Terraforma still exhibits good system usability and does not pose cyber sickness concerns. In conclusion, Terraforma is an effective approach for extending 360 VR to support viewpoint translation and collaboration without increasing acquisition cost of real-world scenes. Some future work may focus in the direction of more effective ways of diluting the viewpoint change, appearance integration of the virtual objects, and extensions to dynamic scenes. That's all for our talk. Thank you so much for listening. For more details and results, please refer to our paper.